Hi, everyone. So my name is Theophan. I'm a Swift developer at Script. And I want to talk about how to maintain a dependency graph with a tool we developed at Script recently, which is called Weather. So yeah, you can find me on Twitter at thrupin. So first of all, what is a DI container? Because that's something we're going to talk about a lot, and that's something that Weather is using a lot as well. So a DI container is basically just an object able to instantiate, retain, and resolve other objects' dependencies. So it comes handy when you need to inject a lot of dependencies into a Swift type, a type. And so the idea is just to kind of bundle a lot of dependencies all together into one object and then pass this object down to other objects. And this way you can kind of mutualize your dependency injection. Then I'm going to talk a lot about dependency graphs in this talk. So that's a dependency graph where foo depends on bar and bar depends on foo. That's pretty obvious. That could be the code for it. So that's the delegate part end pretty much. Where we have bar using foo with a weak variable, and then foo using bar with a strong variable. So this doesn't provoke a retain cycle. And something which is interesting here is that when we look at the dependency graph, as soon as we see this type of shapes, cyclic dependencies, we can think about what's happening under the hood in terms of memory. And here, for instance, without the weak reference, there would be a retain cycle. And when graphs gets bigger, it's sometimes really hard to catch that. Here it's pretty obvious. So let's talk a little bit about Weather. So you can find Weather on GitHub on the script GitHub repository. And Weather is basically a code generation tool, which makes it easy to inject dependencies. So I want to insist on the fact that it's really a tool that it's going to generate a bunch of boilerplate code for you so that you can do your dependencies injection by using this generated code. And so all this happens before the compilation. So it's not actually a framework that you import in your project. You only import the generated code. So why did I think about doing this? Basically because when I looked into it probably 6-7 months ago, it was not really out there. Now there are few libraries that do that. Like I think Uber made one, which is called Needle. But at the time it wasn't existing, and so I just thought, why are we actually doing DI all at runtime? Why wouldn't we do it all at compile time? And so I thought I was going to give it a try. So while building Weather, I found several advantages with doing everything at compile time. First of all, it mimics, in the end, a manual DI technique. So it's only generating code that you could have written yourself. So in some sense, there is no black box. There is no runtime magic. It's only you can go through the code and see what's happening and see what dependencies is in what container, and it's pretty straightforward in the end. There is no compile time errors. There is no runtime errors, so there's only compile time errors, which makes sense. So it fails fast, like when you're trying to inject dependency in some types in your project and the dependency is not there, or for some reason you can't really inject it there. Then Weather is going to tell you, and you're going to see pretty fast what's not working. It's also entirely type safe. If it compiles, it works. The declarativeness. So Weather is working around annotations. So the principle is that you annotate your code, and through annotation, you can inject dependencies in your type, and you can provide dependencies throughout the project. And I found out that it's a pretty cool way of like declare your dependencies, and it's pretty cool to be able to, if you want to know where a dependency is used, just to look for the annotation, and then you have an exhaustive list of where it's used in your project, and also to, if you want to see like what type is using, what dependency the type is using, then you just look in the type in your code, and you have an exhaustive list just by looking at the annotations. Also, all the code that's generated has no optionality, which means that that's what Patrick mentioned as well. When you declare a dependency and you run your code, you know it's there, so you don't have to check or to guard or anything like that. And it's entirely thread safe because the containers that Waver generates are totally immutable, and there is no lazy loading. And also, a good point is that there is no framework to ship. You only ship the generated code in the end. So if you want to drop Waver at some point and stop generating the code, you can. Some few drawbacks that I figured out as well. It's obviously more code to compile, because for each type that are going to have injections with Waver, Waver is going to have to generate few types to undo that correctly. That's something that could be optimized. Waver, in the end, provides a way for you to provide your own templates, so you can actually generate your own code. And if you want to support another type of dependency injection than dependency container, which is pretty heavy, like something like Patrick presented, for example, you could do that. So there's a way of optimize this. Metaprogrammation can be hard and kind of problematic. Then it's also using pseudo annotations, which can be a problem because it's not fully supported by Swift yet. And it's also, at the time, pretty experimental, to be honest. We're not using it at Scrib like very widely. We're starting to use it, but and we're definitely thinking about it, but still pretty experimental, and we'll see how it scales with time. So let's see in practice. I wanted to go through in this talk to go through an example. So here is the example I'm going to talk about. It's a simple application. It's a list of movies, and when you tap on a movie, you can see the description. And what's interesting is that in the description there is an image. We're going to see why. So let's see the dependency graph, a pretty logical dependency graph for this application. So first of all, the root type would be the app delegate. The app delegate would build a home view controller, which would contain the movies. To load the movies home view controller, we need a movie manager, let's call it this way. The movie manager would need to reach a server through the API client, and then the API client would need to perform HTTP request with the URL session. Same thing with the movie view controller and image manager. And so the question is, how could we provide URL session? Because in all these objects here, URL session is the only one that has a state, because there is a HTTP cache. So you kind of want to share the configuration of the URL session and the cache throughout the code base. So that's why there is this link in between app delegate and URL session. App delegate depends on the URL session because it's actually in this graph providing URL session for the entire code base. So how could we share this instance of URL session? So first of all, we could use, I think pretty much all of us have done that before, some kind of singleton using the UI application shared instance. exposing a shared instance of app delegate, and then exposing an instance of your session with the right configuration. One of the problems with that we can see straight away is that we're going to expose your session to the entire code base, and actually only API client is going to use it. So that's a first issue. How would we use this? We would just use the shared instance directly and perform the data task. So it's pretty easy, but in terms of dependency graph, it's not super nice. It would create this weird shape where API client depends on app delegate, and that doesn't look good. So how could we try to inject an instance of your session in the API client? We could, as Patrick was saying, just declare a private let of your session, inject it from the initializer, and then use it. And you notice that here, we set a default parameter, and most of the time that's what developers do, because at the call site, there is most likely no your session to provide to the API client when we build it. And so it's practical to use this default initializer. So when we use it, for example, in Movie Manager, we don't have the URL session, so we don't pass it in, and we just use the default initializer, the default parameter. So in terms of dependency graph, that's the exact same problem in the end, because we're using the same static here, and so it doesn't change anything to the problem. But it's still a little bit better, because now you can inject a different URL session for testing, and you can start to mock your URL session if you want to. You would have to add a protocol, a URL session protocol, or something like that, but it sounds pretty doable. But that's not really where I want to go. So let's try to pass down an instance of the URL session throughout the entire graph, from the app delegate to the API client. So that means that in the API client, there are no default anymore. We're enforcing that they need a URL session to be there when we're going to create this API client. And then, so from Movie Manager to API client, we would need a URL session as well. So we would inject it from the initializer, pass it down to the API client. Same things from the view controller to the Movie Manager, inject it from above, and passing it down to the Movie Manager this time. And then in the app delegate, you're in your root type, so there's no call site. So you can obligate it to create your URL session and pass it down to the view controller. And it turns out that it works pretty well. That's exactly where we wanted to go. So I didn't represent, of course, that view controller depends on your session, because the initializer has the URL session type in it. So I didn't create the links for that, because in the end, view controller is only passing down the instance. It's not really using it. So yeah. So why is this better? In short, because it's a lot more modular. For example, what if Image Manager needed a bigger HTTP cache? And then we could just, in Image Manager, create our own URL session, instead of using the ones that would have been passed on, if we would have respected the same pattern for Image Manager as well. Instead of injecting it from above, we would just create our own, put a bigger cache, because image in general use more data and more space, and we would just pass it on to API client, and we would be pretty much done. The API client wouldn't have to know anything else, and only the image manager knows that the URL session for images have a bigger cache. So we're pretty much just creating a new link here, and that's it. So it's pretty modular. In terms of testability, that's the same thing when we try to, for example, if we wanted to test the API client, we would just have to, as I said before, pass a a mock of your session, and that would work. This is great. Like, all these are nice DI techniques, but it's a little bit too much code to write, because if we had to pass down all the dependencies of the entire project to the first class, like from the app delegate to the root view controller, and then from the root view controller to all the dependencies of the root view controller, etc., it's a lot of code to write, and it's huge initializer to write. So yeah, I kind of ran out of the ideas, but I would expect in a regular size project this to be an initializer of maybe 100 classes, even more. So it doesn't work that well. And that's where Weaver comes handy, because it's going to generate these initiators for us. So just to come back to what we've just done, what methodology have we used? We just looked at the code. We built a representation of the dependency graph for each step. We made sure the dependency graph was OK and fitting our architecture. And we used the DI technique to implement the graph. Well, Weaver does the same, but automatically. It scans the code looking for annotations. It builds a representation of the dependency graph in memory. It validates this dependency graph, so it's looking for cyclic dependencies, unresolvable dependencies, this type of stuff, and it's going to fail at compile time if there is something wrong with it. And it's going to generate the code to implement the graph in the end, and you're going to be able to use this code in your code base. So let's go back to our example and try to achieve the same thing, but with Weaver, so that I can show you like how it works. So first of all, we need to reference your session in API client. To do that, the first step is to use the Dependencies Object, which is an API client dependency resolver. I'm going to show the generated code right after this slide, so I explain this after. But the idea is that dependencies is actually the dependency container I was talking about. We inject it as always with initializer. And then we declare a reference on your session. So Weaver is always going to look for comments beginning with Weaver colon. And so that's how it knows it's an annotation. And so this one is the reference, and then we can use it through dependencies. That's your session. So this one is a reference because we don't actually want to create your session in this class. We want it to inject it. We want to inject it, so we want it to be passed on from the call side. Here's the generated code that Weaver is going to generate for us. So the input dependency resolver is just what the API client needs to build. The API client dependency resolver is what the resolver exposes, what dependencies are exposed to API client. And then the API client dependency container is actually the implementation of the resolver. So let's register API client in Movie Manager. So this time, same thing, we're going to use the dependencies, inject them through the initializer, and we want this time an instance of API client in Movie Manager, so we're going to use this annotation instead with the equal, saying that we're creating an instance, and then we can use it through the dependencies like this. This time the generated code is going to be still the requirement for building this class is going to be to have a URL session as an input. What we expose this time is the API client to the class, and then the implementation where there is a builder for API client, and URL session is passed on from the call site. So that's what you can see in the initializer, and that's what it's getting from the input dependency resolver. So this is the exact same thing. It's very repetitive. So we want to use the movie manager and the home view controller, so we do the exact same thing. The code is going to look pretty much the same. And in the end, we try to compile. And so what's going to happen is that weather is going to tell us that your session is missing because we actually never created an instance of your session anywhere. So let's look at what weather is doing. So in the graph, we started from the app delegate. We went to OnView controller, then movie manager, then API client. API client is trained to use your session. So weather is going to check that your session exists. It's going to check if it exists in API client. It's not. It's going to backtrack to movie manager. It's not in there. To OnView controller, it's not in there. And in the end, it's not in app delegate either. There's no way to go. So your session is missing. So let's register your session in the app delegate. This time we use the app delegate dependency container because weather can't create the app delegate class for us since it's a root type. So we can bootstrap this manually. Then we declare your session this way. We're going to set a scope on it just so that the URL session is not built several times. It's actually built once and then stored so that we can take advantage of the HTTP cache. And then the URL session has its own initializer, so Weather doesn't know about it, so we need to use a specific builder. So that's what this static is for. We build the URL session, and then the app delegate also needs to declare the OnView controller, since that's going to be the root controller. So let's look at the generated code. This time there is no input, since the app delegate is not built by Weather. And so there is only, the resolver is going to only expose the OnView controller, since the URL session is actually not used in the app delegate, it's only passed on. And the container is going to have one instance of URL session, which is instantiated with the make URL session static function in the initializer. And it's going to be able to provide the OnView controller by injecting the OnView controller dependency container. And so in the end, we just did pretty much the same thing that we've done before, but with Weather. The only difference is that the generated code is using DI containers automatically. We haven't so it kind of adds an extra layer, but these containers come really handy when there's a lot of dependencies to maintain. And yeah. Is it still modular? Yes, it is. So let's get back to our example where we want to switch the URL session in the image manager. So the only thing we would do is still using the same dependencies object, and then we would declare the URL session the same way we've declared in the app delegate. And we would, this way we are overriding in the graph, in this path of the graph. So in the path of the graph passing by image manager, we're adding a link here. So the same link I was talking about before. And we're overriding the instance of URL session with one that has a bigger cache. In terms of generated code, I'm not going to go through this because it's pretty much the same thing than the generated code for the app delegate. And so, yeah, it works out of the box as well. It's pretty easy. So that kind of shows you how Weather can be used and how Weather can guide in a project, can guide developers or to inject dependencies and or where to get them, how to avoid like cyclic dependencies, these type of things, by just adding annotations to your type and then let Weather do the job for you. There is obviously room for improvement. So the first step would be to adopt whether more widely a script and see how it scale and start resolving like problems that we could have when integrating it in a large code base. Some other improvement could be to make a dependency graph visualizer out of it. We could try to perform like dependency graph optimizations, try to detect weird shapes and try to tell to the developers how to reorganize their code so that the dependency graph is a little bit more optimized. It could be used to detect retain cycles, for example, and avoid like memory issues. Yeah, and what I just said, like it could detect like suspicious graph shapes and warn the developer, and probably more than that. So yeah, that's all for me. Thank you for listening.
Any questions? We have time for 3 questions again.
How does this work with tests?
So yeah, I haven't really talked about that. So if you look here, for example, yeah, for example, we were talking here about the image manager. So if you want to test the image manager, for example, here, you would just have to create a mock implementation or a stub implementation of the image manager dependency resolver, which would kind of force you to provide as well a stub implementation of the URL session. And then you would be able to unit test your image manager by injecting a stub implementation of your URL session. So, and since this standard is followed for every types using dep.di with Weaver, pretty much everything is testable out of the box.
Thank you.
Hi, can you explain a little bit about what you used for the code generation and how that's affected like compile times and like the developer experience around that?
Yeah, so for the code generation, I use singleton, which is based on SourceKit. It's just a bridge. So basically what it's doing, it's scanning the code. SourceKit gives you all the information about the structure of the code. So then Weaver just goes through the structure, detect where the annotations are, in what types, etc. Builds the entire dependency graph out of that, and then is all happening in memory out of the dependency graph.
We can have one more question. Okay, thank you very much, Theo Fen.
Thank you.